Hello everybody, good morning. Today we're going to be looking at the last bit of our notes on chapter 7 and 8, rotational kinematics and dynamics. And the last thing we're going to be looking at is angular momentum. Now we already know that an object that is moving in a straight line has linear momentum, P, and that equals the mass times the translational or linear velocity, V. A body that rotates about a fixed axis also has angular momentum, and we use a capital L to denote angular momentum. It is also measured in kilogram meters per second. It is the product of the body's moment of inertia and its angular velocity with respect to the rotational axis. So L equals I omega. This is again analogous to linear or translational momentum. So here we have angular momentum, here we have linear momentum. Here we have moment of inertia, here we have its analogous mass. Here we have angular speed, here we have linear or translational velocity. And I should have said angular velocity right there. Okay, so this is how we would find angular momentum L, moment of inertia times the angular velocity. Now, just like with linear momentum of an isolated system, the angular momentum of an isolated system is also conserved. The total angular momentum of a system remains constant if the net average external torque acting on the system is zero. Just like for a linear system, if the net external force is zero, momentum is conserved. Here, since torque is analogous to force, then if the net external torque acting on the system is zero, momentum is conserved. Okay, so the internal torques have no effect on angular momentum of an isolated system. Only external torques do. So if we say the sum of the angular momentum at the beginning of an event must equal the sum of the angular momentum at the end of an event or at any other point in time as well. Again, analogous to our linear or translational conservation of momentum. So let's look at this little question. This is a very classic question. It says, when an ice skater spins in place on her skates, she spins faster and faster when she pulls her arms in. And you may have seen that quite often watching the Olympics or any of the other skating competitions on TV. When the skater pulls her arms in towards her body, she speeds up when she spins on her skates. Why does this happen? Okay. Her angular momentum must stay constant. So when she brings her arms in, she's decreasing her radius of rotation and therefore, or hence, her moment of inertia. Because remember, moment of inertia depends on R. So if R decreases, the moment of inertia must decrease. But in order for the momentum to stay constant, if her moment of inertia decreases, then her angular speed must increase for the product that yields the momentum to be the same. So I put it down here mathematically. If we solve for the angular speed and the momentum stays constant, if we assume a person to be a tall solid cylinder with a moment of inertia of 1/2 mr squared, you can see here that when the mass and the momentum are constant, as R decreases, then the angular speed must increase for momentum to be conserved. So we have a inverse square proportion here. So when the radius of the mass, rotating mass decreases, the angular speed must increase. Likewise, if the radius of rotation of the mass increases, then the angular angular speed must decrease. And that is so that the product L, the angular momentum, stays constant. Short little lesson on that. I'm going to include some example problem videos in your folder that you can look at, and of course your assignment. All right, talk to you later. Bye-bye.